Welcome back to class. Today, we are moving forward in Chapter 7, Quadratic Equations and Their Applications. In this specific lesson, we will cover the remaining three core areas, Section 7.4, Quadratic Graphs, Section 7.5, the Discriminate, and Section 7.6, Motion Tasks and Other Applications. Let's focus on these advanced algebraic concepts. Section 7.4. The graph of any quadratic function forms a smooth curve called a parabola. When the coefficient is positive, the parabola opens upward, forming a U-shape. When it is negative, it opens downward, forming an N-shape. Every parabola is perfectly symmetric across its vertical line of symmetry. Now, let's explore how the exact size of a changes the graph. A bigger value of the absolute value of a results in a steeper or narrower parabola. For instance, notice how the blue graph of y equals 2x squared is much steeper and narrower than the original red graph of y equals x squared. Section 7.4. The graph of y equals ax squared plus c has the exact same shape as y equals ax squared. The only difference is its vertical position. Adding a constant c moves the entire parabola up or down along the y-axis. Let's look at these fresh examples on our coordinate plane. An important property of these graphs is how they cross the x-axis. The points where the graph crosses the x-axis are called the x-intercepts or roots. For example, y equals x squared minus 9 crosses the x-axis at exactly plus or minus 3. However, the graph y equals x squared plus 2 never crosses the x-axis at all, because the equation x squared plus 2 equals 0 has no real solutions. Section 7.4. To accurately graph any quadratic function of the form y equals ax squared plus bx plus c, there are three essential features you need to find. First, find the x-intercepts by solving the quadratic equation when y equals 0. Second, find the y-intercept by setting x equal to 0. Third, determine the exact position of the vertex. Let's look at example 1 with fresh numbers. Sketch the graph of y equals x squared minus 4x plus 3. First, setting y to 0 gives the roots x equals 1 and x equals 3, which are our x-intercepts. Second, setting x to 0 gives y equals 3, our y-intercept. Third, completing the square reveals the vertex is at the point 2, -1. Now, let's watch these key elements form a beautiful parabola on the left. Section 7.4. Let's try to sketch the graph of y equals x squared minus 4x plus 5. First, if we attempt to find the x-intercepts by applying the quadratic formula, we notice something unusual. The value inside the square root becomes -4. Since we cannot take the square root of a negative number in real numbers, this tells us the function has no real roots and never crosses the x-axis. But this doesn't mean that we cannot graph it. We just need a different method. The trick is to complete the square to find the vertex. Rewriting the equation gives y equals x minus 2 squared plus 1, which clearly shows our vertex is located at the point 2, 1. Let's look at the left to see this parabola opening upward, completely above the x-axis. Section 7.5. We can use the quadratic formula to find the x-intercepts of a parabola. By setting y equal to 0, finding the solutions to the quadratic equation allows us to see exactly where the graph crosses the x-axis. In fact, the value of b squared minus 4ac under the radical tells us a lot about these solutions. However, it is sometimes impossible to get a real answer from the formula. When b squared minus 4ac is negative, we cannot take the square root of that number. Geometrically, this means that the function has no real roots, and the graph of the parabola never crosses the x-axis at all. Section 7.5. Let's describe the nature of the solutions for the equation 2x squared minus 5x minus 3 equals 0 and find their exact values. First, listing our coefficients gives a equals 2, b equals negative 5, and c equals negative 3. Calculating the discriminant b squared minus 4ac results in 49. Since 49 is positive, the equation has two distinct real solutions. Applying the quadratic formula, we find x equals 3 or negative 1/2. Because our discriminant was positive, the corresponding function graph must cross the horizontal x-axis at exactly two places. These cross points match our calculated roots perfectly. Let's look at the left coordinate plane. You can clearly observe the blue parabola passing through 3, 0, and negative 0.50. Section 7.5. Next, let's explore what happens when b squared minus 4ac equals 0. If the discriminant is exactly 0, then the solutions of the quadratic equation are real and equal to each other. This is also commonly called a double root. Graphically, it means the parabola just touches the x-axis in one place. Let's look at example 3 with creative new numbers. Determine the nature and find the values of the solutions for x squared minus 4x plus 4 equals 0. Computing b squared minus 4ac gives negative 4 squared minus 16, which is 0. This tells us the equation has a double root. Factoring reveals the single solution x equals 2. On the left, you can watch the blue parabola touch the x-axis perfectly at the point 2, 0. Section 7.5. Let's finish our discriminant case studies by looking at what happens when b squared minus 4ac is less than 0. If the discriminant is negative, the quadratic has no real solutions, and the function has no real roots. Graphically, this means the parabola never intersects, crosses, or touches the x-axis. Let's describe the graphs for two creative examples. Equation A is x squared minus 2x plus 2. Its discriminant is negative 4, and since it is positive, the graph is concave up and stays entirely above the x-axis. Equation B is negative x squared plus 4x minus 5. Its discriminant is also negative 4, but since it is negative, the graph is concave down and stays entirely below the x-axis. Section 7.6. Quadratic functions can beautifully describe motion under gravity. Suppose the height of a stone thrown up in the air is modeled by the equation h equals 96t minus 16t squared. We want to find out after how many seconds is the stone at a specific height of 128 feet. Let's solve this quadratic application puzzle. To solve this, we first rewrite the equation in standard form, giving 16t squared minus 96t plus 128 equals 0. Next, we divide through by 16 to simplify the equation, which yields t squared minus 6t plus 8 equals 0. Factoring this quadratic equation gives open parenthesis t minus 2 close parenthesis times open parenthesis t minus 4 close parenthesis equals 0. By the zero product property, we find t equals 2 or t equals 4. So the stone reaches 128 feet after 2 seconds on the way up, and again after 4 seconds on the way down. Section 7.6. Let's analyze an advanced word problem. The height of a ball in feet after t seconds is given by the function h equals negative 16t squared plus 64t plus 80. First, let's explain what the h-intercept and t-intercept mean in this context. The h-intercept represents the initial height of the ball before release, which is 80 feet. The t-intercept indicates the time when the ball hits the ground, which is 5 seconds. Now let's find the maximum height reached by the ball. To do this, we rewrite our function into the vertex form by completing the square. This gives h equals negative 16 times the square of t minus 2 plus 144. This clearly reveals that the vertex is at the point 2, 144. Therefore, the ball reaches its maximum height of 144 feet after exactly 2 seconds. Let's look at the left to watch this stunning parabola launch from 80 feet, hit peak, and fall down.